Tonight, we're going to explore the most violent thing that can happen in the universe. Not a supernova, not a black hole swallowing a star. Something far, far worse. Imagine an explosion so powerful that in a single second it releases more energy than our sun will produce in its entire 10 billion year lifetime. An explosion so focused, so concentrated, that if one occurred within a few thousand light years of Earth, pointed in our direction, it could devastate our ozone layer and trigger a mass extinction. These events are real. They happen somewhere in the observable universe roughly once every day. They're called gamma ray bursts, and the physics behind how they work, how a dying star or a collision between two impossibly dense objects can produce the most extreme explosion we've ever detected, is genuinely one of the most extraordinary stories in all of science. Before we dive in, if you find these kinds of deep explorations of the universe interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with death. Specifically, the death of a star. Because to understand the most violent explosion in the universe, you first need to understand what a normal stellar death looks like. And even a normal stellar death is already one of the most extreme events you can imagine. Stars are not eternal. They seem that way from our perspective down here on Earth. The sun rises every morning, sets every evening, and has done so for as long as humans have existed. But stars are born, they live, and they die. Every single one of them. The sun will die. Sirius will die. Every star you can see in the night sky will eventually exhaust its fuel and come to an end. The only question is how they die. And the answer depends almost entirely on one thing. Mass. How much stuff the star is made of. A star like our sun, which is a pretty average star, will die relatively quietly. It has enough hydrogen fuel in its core to keep burning for about 10 billion years total. It's about halfway through that lifespan right now. When the hydrogen in its core runs out, the sun will swell into a red giant, expanding until it engulfs Mercury and Venus, and possibly Earth. Then it will shed its outer layers gently into space, creating a beautiful glowing shell of gas called a planetary nebula. What's left behind will be the exposed core, a dense ball about the size of Earth, but containing about half the mass of the original star. This is called a white dwarf. It will glow faintly from residual heat, slowly cooling over trillions of years until it becomes a cold, dark cinder drifting through space. That's a quiet death. Gentle by cosmic standards. Dramatic from a human perspective, sure, but in the grand scheme of the universe, it's unremarkable. But not all stars die quietly. Stars that are much more massive than the sun, stars with 8 or more times the sun's mass, die violently. Extremely violently. These massive stars burn through their fuel much faster than smaller stars. This seems counterintuitive at first. You might think a star with more fuel would last longer, but the opposite is true. A more massive star has a more massive core, which means more gravitational pressure crushing inward, which means higher temperatures and pressures at the center, which means nuclear fusion runs at a dramatically faster rate. A star with 20 times the mass of the sun doesn't live 20 times longer. It actually lives far shorter because the pressure and temperature at its core are so much higher that it fuses hydrogen at an enormously accelerated rate. A star like that might live only 10 million years compared to the sun's 10 billion. That's 1,000 times shorter. These massive stars live fast and die young. They burn with incredible ferocity, blazing blue weight across the sky, pouring out light and energy at rates that dwarf anything our sun can produce. And then, after just a few million years, they die in catastrophic fashion. And when they die, they don't go gently. They explode. The explosion is called a supernova, and it is one of the most powerful events in the known universe. A single supernova can briefly outshine an entire galaxy. Think about that for a moment. A galaxy contains hundreds of billions of stars, and one dying star, for a few weeks, can produce more light than all of those hundreds of billions of stars combined. The energy released in a supernova is almost beyond comprehension. A typical supernova releases about 10 to the 46 joules of energy. That number is so absurdly large that it's meaningless to most people, so let me put it in perspective. The sun produces about 3.8 times 10 to the 26 joules of energy every second. That's already an enormous amount. It's enough to power all of human civilization billions of times over. But a supernova releases more energy in a few seconds than the sun will produce in its entire 10 billion year lifetime. In fact, the total energy from a single supernova exceeds the sun's entire lifetime radiative output by more than 100-fold, all compressed into a brief, catastrophic moment. So how does this happen? What makes a massive star explode? The answer lies in what's happening inside the star's core during the final stages of its life, and this process is genuinely fascinating. A star is essentially a battle between two forces: gravity, which wants to crush the star inward, and the outward pressure generated by nuclear fusion in the core. As long as fusion is producing energy, the star remains in balance. Gravity pushes in, pressure pushes out, and the star holds its shape. This balance is called hydrostatic equilibrium, and it's what keeps every star stable for most of its life. In a massive star, fusion starts with hydrogen, just like in our sun. Hydrogen atoms fuse together to form helium, releasing energy in the process. This is what the sun is doing right now. But in a massive star, the temperatures and pressures at the core are much higher, so this process happens much faster. When the hydrogen in the core is exhausted, something different happens compared to a sun-like star. Instead of simply swelling up and dying gently, the massive star's core contracts under gravity, which heats it up even further. The temperature rises high enough for the helium to start fusing into carbon, so now the star has a second life, burning helium in its core while hydrogen continues to burn in a shell around it. But helium runs out too, and when it does, the core contracts again, heats up again, and carbon begins fusing into neon. Then neon fuses into oxygen. Then oxygen fuses into silicon. Each new fuel ignites at a higher temperature than the last, and each stage lasts for a shorter time. The hydrogen burning phase lasted millions of years. The helium burning phase lasts hundreds of thousands of years. Carbon burning lasts maybe a few thousand years. Neon burning lasts about a year. Oxygen burning lasts a few months. And silicon burning, the final stage, lasts only about a single day. During this process, the star develops an onion-like structure. Each layer is burning a different element. The outermost layer is still fusing hydrogen. Beneath that is a shell of helium fusion. Then carbon, neon, oxygen, and finally silicon at the very center. Each inner layer is hotter and denser and producing heavier elements. If you could somehow slice the star open and look at a cross-section, you'd see these nested shells of fusion, each one operating at a more extreme temperature than the one above it. The outermost hydrogen-burning shell operates at about 20 million degrees. The silicon-burning core, the innermost shell, operates at roughly 3 billion degrees. The temperature at the center of this dying star is about 200 times hotter than the center of our sun. And all of this is happening inside a single star, as a star that from the outside might look like just another bright point of light in the sky. Silicon fuses into iron, and this is where everything changes, because iron is special. Iron is the most tightly bound nucleus in nature. When lighter elements fuse together, energy is released. That's what powers stars. But iron is at the bottom of the energy curve. Fusing iron into heavier elements doesn't release energy. It requires energy. It absorbs energy. So when the core fills with iron, the star has a fundamental problem. It can no longer generate energy through fusion. The engine that has been holding the star up against gravity for millions of years has just shut off. What happens next occurs in less than a second. And when I say less than a second, I mean it. The entire core of the star, a ball of iron roughly the size of Earth, containing about 1.5 times the mass of the Sun, collapses in about a quarter of a second. Without the outward pressure from fusion to hold it up, gravity wins instantly and completely. There's no gradual decline. There's no slow fade. The support vanishes, and the core implodes at speeds reaching 70,000 kilometers per second. That's roughly a quarter of the speed of light. In that fraction of a second, the core compresses from something the size of Earth to something the size of a city, roughly 20 kilometers across. The density becomes so extreme that atoms themselves are crushed. Protons and electrons are squeezed together so hard that they merge, forming neutrons and releasing neutrinos in the process. The entire core becomes a ball of neutrons about 20 kilometers across. This is a neutron star, an object so dense that a sugar cube-sized piece of it would weigh about 1 billion tons on Earth. More than every car, truck, ship, and building on the planet combined. Compressed into a volume you could hold in your hand, the infalling material from the outer layers of the star crashes into this newly formed neutron star and bounces, hard. A shockwave rips outward through the star. At the same time, an enormous burst of neutrinos, ghostly subatomic particles that barely interact with matter, floods outward from the core. These neutrinos carry away about 99% of the total energy released in the collapse. The shockwave, energized by the neutrinos and the bounce, tears the star apart from the inside out. The outer layers are blasted into space at speeds of tens of thousands of kilometers per second. This is the supernova. What's left behind depends on how massive the original star was. If the core is below roughly 2 to 2.5 solar masses, it stabilizes as a neutron star, an object so dense that even a teaspoon of its material would weigh billions of tons on Earth. If the core is more massive than that, even the pressure between neutrons can't hold it up, and it collapses further into a black hole, a point of no return where gravity becomes so strong that not even light can escape. Now, a supernova is already an extraordinarily violent event. It's the most powerful explosion most people have ever heard of. It can outshine an entire galaxy. It forges heavy elements and scatters them across space. It's one of the most important events in the universe because without supernovae, there would be no carbon, no oxygen, no iron, no rocky planets, no life. Every atom in your body heavier than hydrogen and helium was forged either in the core of a massive star or in the supernova explosion that ended that star's life. You are literally made of the debris from ancient stellar explosions. So supernovae are already extreme. They're already almost beyond comprehension in terms of the energy they release and the violence of the process. You might think that nothing could be more powerful. You would be wrong. Because starting in the 1960s, astronomers began detecting something that made even supernovae look almost gentle by comparison. And the story of how they found it is remarkable in itself. In 1963, the United States and the Soviet Union signed the Partial Nuclear Test Ban Treaty, which prohibited nuclear weapons testing in the atmosphere, in outer space, and underwater. To verify compliance, the United States launched a series of military satellites called the Vela satellites. These satellites were designed to detect the gamma radiation that nuclear explosions produce. If the Soviets secretly detonated a nuclear bomb in space, the Vela satellites would see the flash of gamma rays and catch them in the act. The satellites worked beautifully. They were sensitive instruments capable of detecting bursts of gamma radiation from any direction in space. And they did detect bursts, but not from Soviet nuclear tests. Starting on July 2nd, 1967, the Vela satellites detected a brief, intense flash of gamma rays coming from somewhere in space. It didn't match the signature of a nuclear explosion. It didn't match anything anyone had seen before. It was a short burst of the highest energy form of light in the universe, lasting only a few seconds, and then it was gone. The military classified the detection. Over the next few years, the satellites detected more of these bursts. 16 in total by 1973. Each one was different. Some lasted a fraction of a second. Others lasted tens of seconds. They came from random directions in the sky with no apparent pattern. And they were clearly not nuclear weapons. They didn't have the right signature. They didn't come from the right places. Whatever these were, they were natural phenomena. Something happening out there in the cosmos that nobody had predicted or expected. In 1973, the discovery was declassified and published in a scientific paper by Ray Clevesidel, Ian Strong, and Roy Olson at Los Alamos National Laboratory. The paper was titled Observations Gamma Ray Bursts of Cosmic Origin. It announced to the world that something out there in space was producing brief, intense flashes of gamma radiation, and nobody had any idea what it was. This paper launched one of the great detective stories in modern astronomy. For the next quarter century, gamma-ray bursts would remain one of the deepest mysteries in astrophysics, spawning hundreds of theories and intense scientific debate. Now, let me explain why gamma rays are important here. Because the type of light these bursts produce tells us something crucial about how violent the events are. Light comes in many forms. What we see with our eyes, visible light, is just a tiny slice of the electromagnetic spectrum. Below visible light in energy, you have infrared, microwaves, and radio waves. Above visible light in energy, you have ultraviolet, then X-rays, and at the very top, the most energetic form of light possible, gamma rays. Gamma rays are produced by the most extreme processes in the universe. They come from nuclear reactions, from matter falling into black holes, from particles being accelerated to nearly the speed of light. When you detect a burst of gamma rays from space, you know immediately that something incredibly violent has happened. Something involving temperatures of billions of degrees, or particles moving at velocities very close to the speed of light, or both. Gamma rays are the calling card of extreme physics. And these bursts were producing enormous amounts of them. For decades after the initial discovery, Gamma-ray bursts remained one of the biggest mysteries in astronomy. The fundamental question was simple but unanswered. How far away are they? And this question mattered enormously, because the distance would determine how much energy was involved. Think about it this way. If you see a bright light in the sky, it could be a nearby flashlight or a distant searchlight. If it's a flashlight 10 meters away, it's producing a modest amount of light. If it's a searchlight 10 kilometers away, it's producing an enormous amount of light. The apparent brightness is the same, but the actual energy output is vastly different. The same logic applied to gamma-ray bursts. If they were happening nearby, within our own galaxy, then they might be interesting but not extraordinary in terms of energy. But if they were happening far away, in distant galaxies, then the energy involved would be almost unimaginable. For years, astronomers couldn't tell. Gamma-ray bursts appeared randomly across the sky, which didn't match what you'd expect if they came from within the Milky Way. If they originated in our galaxy, you'd expect to see more of them concentrated along the plane of the Milky Way, where most of the galaxy's stars are located. Instead, they came from every direction equally, which hinted that they might come from much farther away, from distant galaxies scattered uniformly across the sky. But nobody could pin down a distance. The breakthrough came in 1997, thanks to an Italian-Dutch satellite called Beppo-Sax. This satellite could detect a gamma-ray burst, and then quickly determine its position in the sky with enough precision for other telescopes to look at the same spot and search for a visible light counterpart. In February of 1997, Beppo-Sax detected a gamma-ray burst and pinpointed its location. Within hours, ground-based telescopes swung to that position and found a fading optical glow. This was the first afterglow, the slowly fading visible light emitted after the initial gamma-ray flash. Afterglows changed everything. They allowed astronomers to identify the host galaxies where bursts had occurred, and when they measured the distances to those galaxies using the redshifts of their light, the way that the expansion of the universe stretches light from distant objects toward the red end of the spectrum, the results were staggering. These bursts were occurring billions of light years from Earth, some at distances of 6 billion light years or more. 6 billion light years. That means the light from this explosion had been traveling through space for 6 billion years before it reached the satellite's detectors. When this burst happened, Earth didn't even exist yet. Our solar system wouldn't form for another 1.5 billion years. The explosion predated our entire world. And even after traveling for 6 billion years, spreading out across an unimaginable volume of space, the burst was still powerful enough to be easily detected by instruments on or near Earth. That fact alone tells you something extraordinary was happening. When astronomers calculated how much energy the burst must have released to still be that bright after traveling 6 billion light years, the numbers were almost absurd. If the energy had been radiated equally in all directions, like a bare light bulb shining the same amount in every direction, then the total energy output would have been enormous. For some of the most energetic bursts, astronomers calculated an isotropic equivalent energy of roughly 10 to the 47 joules. That number is so extreme that it deserves special attention. 10 to the 47 joules is roughly the amount of energy you'd get if you convert the entire mass of the Sun directly into energy using Einstein's famous equation equals mc squared. The entire mass of the Sun, converted completely into pure energy, released in a matter of seconds. To put this in perspective, Remember that a supernova releases about 10 to the 46 joules of total energy, and only about 10 to the 43 joules as visible light. These gamma-ray bursts appear to be releasing 10 to 100,000 times more energy than a supernova's entire light output, all compressed into seconds rather than weeks. For a brief moment, a single gamma-ray burst seemed to outshine the entire observable universe. More energy pouring out of one point in space than all the stars in all the galaxies everywhere combined. This created a serious problem, because astronomers couldn't figure out any physical mechanism that could produce that much energy. There's simply no known process that can convert that much matter into energy that quickly. The numbers didn't work, the physics didn't add up, something was wrong, and something was wrong, not with the observations, but with the assumption. The assumption that the energy was being radiated equally in all directions. It wasn't. This was the critical insight that changed everything and unlocked the true nature of gamma-ray bursts. The energy from a gamma-ray burst isn't sprayed out uniformly like a light bulb. It's concentrated into two incredibly narrow beams, jets of matter and radiation moving at velocities exceeding 99% the speed of light, aimed in opposite directions from the source. These are called relativistic jets, and they change the energy calculation dramatically. Imagine the difference between a bare light bulb and a laser pointer. A light bulb sends light in every direction. If you stand in any position around the bulb, you see roughly the same brightness. The energy is spread out uniformly across the entire sphere surrounding the bulb. A laser concentrates all its light into a narrow beam. If you're standing off to the side, you see nothing. But if you're standing directly in front of the laser, it appears incredibly bright, far brighter than the light bulb, even though the laser might actually be using less total energy. The brightness you see depends not just on how much total energy is being produced, but on how much of that energy is aimed directly at you. A 5 milliwatt laser pointer can appear far brighter than a 60-watt light bulb if you look directly into the beam, even though the bulb is producing 12,000 times more total power. Gamma-ray bursts work the same way. The jet is only a few degrees wide, sometimes as narrow as 1 or 2 degrees. This means the energy is concentrated into a cone that covers only a tiny fraction of the sky. When you account for this beaming, the actual total energy released drops enormously. Instead of 10 to the 54 joules, the real energy output is close to 10 to the 44 to 10 to the 45, the 44 to 10 to the 45 joules. That's still a staggering amount, still comparable to or even exceeding a supernova. But it's no longer physically impossible. It's no longer more energy than the entire sun converted into pure energy. It's still the most violent explosion we've ever detected, but now it falls within the range that known physics can explain. But here's the crucial point. Even though the total energy is lower than originally estimated, the apparent energy, the energy per unit area that hits your detector when you happen to be looking down the barrel of the jet, is genuinely as extreme as those original calculations suggested. If you are in the path of one of these jets, what you experience is the full force of that concentrated beam, and that makes gamma-ray bursts, as observed, the most violent explosions in the universe, not because they produce more total energy than anything else, although they produce an extraordinary amount, but because they concentrate that energy into a beam so narrow and so intense that nothing else in the cosmos comes close. This is the fundamental mechanism. The violence of a gamma-ray burst comes not just from the amount of energy involved, but from the concentration of that energy. It is the difference between being hit by a wave and being hit by a water jet cutter. The total amount of water might be similar, but one spreads its force over a large area, while the other focuses it into a point capable of cutting through steel. A gamma-ray burst focuses the energy of a stellar catastrophe into a beam only a few degrees wide, moving at nearly the speed of light, carrying enough concentrated power to be detected from billions of light years away. And this raises the obvious next question. What creates these jets? What physical process takes the death of a star, or the collision of two impossibly dense objects, and converts it into two narrow beams of matter and energy moving at nearly the speed of light? The answer involves some of the most extreme physics in the universe. Black holes, accretion disks, magnetic fields twisted to the breaking point, and matter compressed to densities that challenge the imagination. The formation of these jets is where the real story of gamma-ray bursts begins. And it turns out, there isn't just one way to make them. There are two completely different catastrophes that produce these explosions, each violent in its own way, each producing the same terrifying result, a focused torrent of gamma rays detectable from the farthest reaches of the observable universe. The first involves the death of the most massive stars in the universe, stars so large they make our sun look like a candle flame next to a bonfire. Stars that contain 25, 40, even 100 times the mass of our sun. Stars so luminous that they can be seen across entire galaxies. When one of these titans dies, under the right conditions, it doesn't just explode as an ordinary supernova. Its core collapses directly into a black hole, and that black hole, feeding on the infalling stellar material, launches jets that punch through the dying star like a bullet through tissue paper. The second involves something even more exotic. The collision between two neutron stars, the ultra-dense remnants of previous stellar explosions, spiraling together over millions or billions of years in a death dance that ends in the most violent impact imaginable. Two objects, each containing more mass than the sun, compressed into a sphere the size of a city, slamming together at a significant fraction of the speed of light. Both paths lead to the same destination. A newborn black hole surrounded by superheated matter, launching jets of material at velocities that seem almost impossible. And both produce the same signature, a brief, blinding flash of gamma rays visible across billions of light years of space. Understanding how each of these paths works, understanding the specific physics that creates these jets and powers these explosions, is the key to understanding why gamma ray bursts are not just big explosions. They are the most violent, most concentrated, most extreme releases of energy that the universe is capable of producing. And the mechanisms behind them are as elegant as they are terrifying. Now we know what a gamma ray burst looks like from the outside. A brief, blinding flash of the highest energy light in the universe, detected from billions of light years away, powered by narrow jets of material moving at nearly the speed of light. But knowing what it looks like doesn't explain how it works. To understand that, we need to go inside the event itself. We need to follow the physics step by step, from the moment a star begins to die to the moment those jets punch through its outer layers and scream into space at relativistic velocities. And to do that, we need to talk about a very specific kind of star. Not just any massive star. The most massive stars in the universe. Stars so extreme that their deaths don't produce ordinary supernovae. Their deaths produce something far worse. The stars we're talking about are monsters, the heaviest stars the universe produces, objects so massive that some of them contain more material than 80 or 90 suns combined. These are rare objects. Out of all the stars in a galaxy like the Milky Way, only a tiny fraction, less than 1%, reach these extreme masses. But their rarity doesn't diminish their importance. In fact, it's these rare, massive stars that shape the universe more than any other type. Let me give you a sense of what these stars are like. Our sun has a diameter of about 864,000 miles. A star with 40 times the sun's mass might have a diameter 10 to 15 times larger. It would be enormously luminous, hundreds of thousands of times brighter than the sun. If you replaced our sun with one of these stars, Earth wouldn't just be uninhabitable, it would be scorched. The light and radiation pouring off such a star would be so intense that the inner planets would be bathed in ultraviolet radiation, powerful enough to strip atoms apart. These stars burn so ferociously that they consume their hydrogen fuel in just a few million years. Some of the most massive ones live less than 3 million years. In cosmic terms, that's practically nothing. The universe is 13.8 billion years old. A star that lives 3 million years exists for less than 1/4000th of the universe's current age. These stars are born, they blaze with incredible intensity, and they die almost immediately on the cosmic timescale. Now, we already talked about how a massive star builds up layers of progressively heavier elements in its core, fusing hydrogen into helium, helium into carbon, carbon into neon, and so on down to iron. We talked about how iron is the end of the road because fusing iron doesn't release energy, it absorbs it. But what we didn't talk about in detail is what happens next in the most massive stars. Because what happens next is different from an ordinary supernova. And that difference is everything. In a normal core collapse supernova, the iron core collapses, forms a neutron star, and the bounce plus neutrino energy drives a shockwave that tears the star apart. The neutron star survives. It sits at the center of the expanding debris, spinning rapidly, incredibly dense, but stable. The neutron star is held up by something called neutron degeneracy pressure, a quantum mechanical effect that prevents neutrons from being squeezed any closer together. This pressure is enormous. It can support a core of up to about 2 to 3 solar masses against further collapse. But in the most massive stars, the core that forms during the final collapse can be heavier than this limit. If the collapsing core has more than about 3 solar masses, neutron degeneracy pressure isn't strong enough to stop the collapse. Nothing is. The core doesn't bounce. It doesn't stabilize as a neutron star. Instead, it keeps collapsing. The matter keeps falling inward, compressing to higher and higher densities, until it crosses a threshold from which there is no return. It forms a black hole. A black hole is a region of space where gravity is so intense that nothing, not matter, not light, not information of any kind, can escape. The boundary of a black hole is called the event horizon. Once something crosses the event horizon, it's gone. There is no force in the universe strong enough to pull it back out. The event horizon isn't a physical surface. It's a mathematical boundary, a point of no return defined entirely by the strength of gravity. When the core of a dying massive star collapses directly into a black hole, the dynamics change fundamentally compared to an ordinary supernova. In a normal supernova, the neutron star acts like a wall. The collapsing material hits it, bounces, and drives the explosion outward. But when a black hole forms, there's no wall. There's no bounce. The material that would have hit the neutron star instead falls directly into the black hole. The energy that would have powered the supernova shockwave is swallowed. In many cases, this means the star doesn't explode at all. It simply collapses. The outer layers of the star fall inward, feeding the black hole, and the star vanishes from the universe with barely a whimper. Astronomers have actually observed this happening. A team monitoring massive stars in nearby galaxies tracked a red supergiant in the galaxy NGC 6946 that briefly brightened in 2009 and then slowly faded over the following years until it vanished completely from telescopic view without ever producing a supernova. The most likely explanation is that it collapsed directly into a black hole, swallowing itself. These are called failed supernovae, and they might account for a significant fraction of all massive star deaths, perhaps 10 to 30%. They're one of the quietest ways a massive star can die. No explosion, no fireworks. Just a star swallowed by its own gravity, leaving behind a black hole and nothing else. But sometimes, under the right conditions, something very different happens. Something far more violent than an ordinary supernova. Instead of a quiet collapse, the dying star produces a gamma-ray burst. And the key factor that determines which outcome occurs, the single most important variable that separates a failed supernova from the most violent explosion in the universe, is rotation. If the collapsing core is spinning, and spinning fast, the collapse doesn't proceed symmetrically. Material falling toward the black hole from the poles, along the axis of rotation, falls in relatively freely, but material falling from the sides, from the equatorial regions, has angular momentum. It's spinning, and that angular momentum prevents it from falling directly into the black hole. Instead, it spirals inward, forming a rapidly rotating disk of superheated material around the black hole. This is called an accretion disk. The formation of this accretion disk is the critical moment. It's the moment when a simple collapse transforms into a catastrophic engine of destruction. Because an accretion disk around a black hole is one of the most efficient energy-producing systems in the universe, far more efficient than nuclear fusion, far more efficient than any process humans have ever harnessed or even conceived of. To understand why, consider how different energy sources compare. Chemical reactions like burning gasoline convert less than a billionth of the rest, mass of the fuel, into energy. That's incredibly inefficient. Nuclear fission, which powers nuclear reactors, converts about 0.1% of the rest mass into energy. Nuclear fusion, the process that powers the sun, converts about 0.7%. These are already impressive numbers. Fusion is millions of times more efficient than chemical burning. But accretion onto a black hole can convert between 6% and 42% of the rest mass of the infalling material into energy, depending on how fast the black hole is spinning. 42%. That means for every kilogram of matter that falls into a rapidly spinning black hole, almost half of that kilogram's mass is converted into pure energy, radiated away before the material crosses the event horizon. That's roughly 60 times more efficient than nuclear fusion. This is why accretion disks around black holes are the most powerful engines in the universe. They can extract more energy from matter than any other known physical process. Here's why. When matter falls toward a black hole, it accelerates. Gravity pulls it faster and faster. By the time it reaches the inner regions of the accretion disk, just outside the event horizon, The material is moving at a significant fraction of the speed of light. As this material spirals inward, friction between different layers of the disk converts orbital energy into heat. The temperatures in the inner accretion disk reach billions of degrees. At these temperatures, the matter emits enormous amounts of radiation, primarily in the form of X-rays and gamma rays. But the energy production goes even further than that. The accretion disk doesn't just radiate heat, it also generates incredibly powerful magnetic fields. The disk is made of ionized gas, plasma, which is an excellent conductor of electricity. As this conducting fluid swirls around the black hole at different speeds, different layers moving at different velocities, it amplifies any existing magnetic fields through a process called the magneto-rotational instability. Small magnetic fields get stretched, twisted, and amplified by the differential rotation of the disk until they become enormously strong. These magnetic fields become the key to everything that follows. Because the magnetic fields don't just sit passively in the disk, they interact with the spinning black hole itself. And this interaction is where the jets are born. A black hole formed from a collapsing stellar core isn't just massive, it's spinning. The collapsing core had angular momentum, and as it contracted, it spun faster and faster, just like an ice skater pulling in her arms. By the time the black hole forms, it's rotating at an enormous rate, and a spinning black hole drags space-time around with it. This is called frame dragging, and it's one of the predictions of Einstein's general theory of relativity. The space around a spinning black hole doesn't just curve, it twists, it rotates. Anything near the black hole, including magnetic field lines threading through the accretion disk, gets caught up in this rotation. The magnetic field lines that thread through the inner accretion disk become anchored to the spinning black hole on one end and to the disk on the other. As the black hole spins, it winds these field lines tighter and tighter, like winding a rubber band around a propeller. The magnetic field lines get twisted into a tight helical structure, a corkscrew of magnetic energy aligned along the rotation axis of the black hole. The poles. Above and below the black hole, along its spin axis, these wound-up magnetic fields create a channel, a funnel of magnetic force pointing straight up and straight down. This magnetic funnel does something extraordinary. It accelerates matter along the spin axis to nearly the speed of light. Material from the inner accretion disk gets caught in the magnetic field and flung outward along the poles at velocities exceeding 99% the speed of light. In some cases, the material moves at 99.9% the speed of light, or even faster. These are the relativistic jets. The process that extracts rotational energy from the black hole to power these jets is called the Blandford-Znajek mechanism, named after the two physicists who first described it mathematically in 1977. It's one of the most remarkable energy extraction processes in all of physics. The spinning black hole acts as a flywheel, storing enormous rotational energy. The magnetic fields act as a brake, tapping into that rotational energy and converting it into the kinetic energy of the jets. In effect, the magnetic fields are stealing energy from the black hole's spin and using it to accelerate matter to nearly the speed of light. The amount of energy involved is staggering. A spinning stellar mass black hole can store rotational energy equivalent to several solar masses converted entirely into energy. Via Einstein's equation, the Blandford-Znajek mechanism can extract a significant fraction of this energy over a timescale of seconds to minutes. That's the power source behind a gamma ray burst, not nuclear fusion, not chemical reactions, not even ordinary gravitational collapse. It's the rotational energy of space-time itself, extracted through magnetic fields and converted into twin beams of destruction. But the jets haven't escaped yet. Remember, this is all happening inside a star. The black hole and its accretion disk are at the center of a star that still has substantial outer layers of helium and heavier elements above them. Even in a stripped-down stellar core, that's a great deal of dense material. The jets have to punch through all of it before they can break free into space. And this is not a trivial process. The jets are narrow, typically only a few degrees wide. They're essentially pencil beams of plasma moving at nearly the speed of light. When they hit the dense stellar material above and below the black hole, they have to bore through it. The jet material slams into the overlying stellar envelope at close to light speed, creating a shock front at the head of the jet. This shock front heats the stellar material to extreme temperatures and pushes it aside, carving a channel through the star. This process takes time. The jet has to drill through thousands of kilometers of dense stellar material. For a typical massive star, the jet needs roughly 10 seconds to punch through the stellar envelope. During this time, the jet is being continuously fed by the accretion disk. Material keeps pouring into the black hole. The magnetic fields keep winding, and the jet keeps firing. If the jet is powerful enough and sustained long enough, it breaks through the surface of the star and erupts into space. The moment the jet breaks free is the moment the gamma ray burst begins, and this moment is spectacularly violent. When the jet emerges from the surface of the star, it's no longer confined by the dense stellar material that had been squeezing it from all sides. It expands slightly, but it's still incredibly narrow and focused, typically spanning only about 2 to 20 degrees. That's a remarkably tight beam. To put that in perspective, the full moon as seen from Earth spans about half a degree. So these jets are only a few times wider than the full moon would appear in the sky. All that tremendous energy, all that material moving at nearly the speed of light, concentrated into a cone not much wider than your thumb held at arm's length. The jet plows into the surrounding space, interacting with any gas or dust nearby. But most importantly, the jet itself is not a smooth, uniform flow. It's turbulent and chaotic. The central engine, the accreting black hole, doesn't produce a steady, constant outflow. Instead, it sputters and varies, sending out blobs of material at slightly different speeds, faster blobs catching up to slower blobs ahead of them. When a faster blob catches up to a slower blob within the jet, the collision creates what's called an internal shock. These internal shocks are where the gamma rays are actually produced. The collisions between different parcels of jet material accelerate electrons to incredibly high energies. These high-energy electrons interact with magnetic fields in the jet and emit gamma rays through a process called synchrotron radiation. They also collide with lower energy photons and boost them to gamma ray energies through a process called inverse Compton scattering. This is a crucial point. The gamma rays in a gamma ray burst are not produced at the black hole or in the accretion disk. They're produced within the jet itself, far from the central engine, as different parts of the jet collide with each other at relativistic speeds. The jet is essentially a beam of kinetic energy, and the internal shocks convert that kinetic energy into radiation. The gamma rays we detect are the product of these internal collisions, not direct emission from the black hole. This is why gamma ray bursts have such complex, irregular time profiles. When you look at the light curve of a gamma ray burst, The plot of brightness over time, it's not a smooth rise and fall, it's chaotic, spiky, full of rapid fluctuations, multiple peaks, sudden rises and drops. Each spike corresponds to a different internal shock within the jet, a different collision between blobs of material moving at slightly different speeds. The complexity of the light curve reflects the chaotic, turbulent nature of the jet itself. After the initial burst of gamma rays, the jet continues to plow into the surrounding interstellar medium, the thin gas that fills the space between stars. As the jet decelerates by sweeping up this external material, it creates an external shock. This external shock produces what astronomers call the afterglow. The afterglow is emission across the entire electromagnetic spectrum, from X-rays down through ultraviolet, visible light, infrared, and eventually radio waves. It fades gradually over days, weeks, and sometimes months. The afterglow was what allowed astronomers to pinpoint the locations of gamma-ray bursts and measure their distances for the first time. The gamma rays themselves are too brief and too imprecisely located to identify a host galaxy. But the afterglow, glowing steadily for days or weeks, can be observed with optical and radio telescopes, allowing astronomers to identify exactly which galaxy the burst occurred in and how far away that galaxy is. This entire process, from core collapse to black hole formation, to accretion disk, to jet launching, to jet breakout, to gamma ray emission to afterglow, is called the collapsar model. The name comes from collapsing star. It was first proposed in detail by astrophysicist Stan Woosley in 1993, though elements of the idea had been discussed by others before him. The collapsar model explains what astronomers call long-duration gamma-ray bursts, those that last longer than about 2 seconds. Most long-duration bursts last between 10 and 100 seconds, though some have been observed lasting over 1,000 seconds, more than 15 minutes of continuous gamma-ray emission. The duration of the burst is determined by how long the central engine, the accreting black hole, remains active. As long as material continues falling into the accretion disk, and the disk continues feeding the black hole, the jets continue firing. When the supply of material runs out, when the star's envelope has either been ejected by the accompanying supernova or swallowed by the black hole, the jets shut off and the burst ends. The longer the supply lasts, the longer the burst. Not every massive star produces a gamma-ray burst when it dies. In fact, the vast majority don't. Several specific conditions have to be met. The star has to be massive enough that its core collapses directly into a black hole rather than forming a neutron star. The collapsing core has to be spinning fast enough to form an accretion disk. And the star has to have lost most of its outer hydrogen envelope before it dies, because a thick hydrogen envelope can smother the jet before it breaks free. This last condition is particularly important, and it's worth understanding in some detail. It turns out that the stars most likely to produce gamma-ray bursts are a special class called Wolf-Rayet stars. These are massive stars that have been stripped of their outer hydrogen layers, either by powerful stellar winds or by interactions with a binary companion star. Wolf-Rayet stars are essentially bare stellar cores, compact and hot, surrounded by very little envelope material. When they collapse, their jets have less material to punch through, making it easier for the jets to break free and produce a gamma-ray burst. Wolf-Rayet stars also tend to retain more angular momentum than other massive stars because losing their outer layers can allow the core to spin faster. The hydrogen envelope, when present, can act as a brake on the core's rotation through magnetic coupling. When the envelope is removed, the core is free to spin up as it contracts, providing exactly the rapid rotation needed to form an accretion disk during collapse. There's another condition that appears to be important: metallicity. In astronomy, metallicity refers to the abundance of elements heavier than hydrogen and helium. Stars with low metallicity, meaning they have fewer heavy elements, tend to have weaker stellar winds. Weaker winds mean the star loses less mass and less angular momentum during its lifetime. This preserves the rapid rotation of the core, which is essential for the collapsar mechanism. This is why long-duration gamma-ray bursts are observed preferentially in small, irregular galaxies with low metallicity rather than in large, metal-rich spiral galaxies like the Milky Way. The stars in these small galaxies have fewer heavy elements, weaker winds, and faster spinning cores. They're the ideal progenitors for gamma-ray bursts. This observational pattern is a strong piece of evidence supporting the collapsar model. If gamma-ray bursts were produced by some other mechanism that didn't depend on metallicity, you'd expect to see them in all types of galaxies equally. But we don't. We see them preferentially in the kinds of galaxies where the collapsar model predicts they should occur. Let me paint you a picture of what this entire process looks like in sequence, from beginning to end, because the timeline is remarkable. A massive star lives for a few million years, burning through its nuclear fuel at a furious rate. In the final stages of its life, the pace becomes almost frantic. Each successive fuel burns faster than the last. What began as millions of years of steady hydrogen fusion compresses into a cascade that ends with silicon burning through its entire supply in a single day. At the end of that day, the core is filled with iron, and the star has reached the end of the line. The iron core collapses. In less than a second, something the size of Earth compresses into a black hole smaller than a city. The material around the black hole spirals inward, forming an accretion disk in a matter of seconds. The accretion disk and spinning black hole generate magnetic fields that wind up and launch two jets along the poles. The jets, moving at more than 99% the speed of light, slam into the overlying stellar material. For roughly 10 to 20 seconds, they drill through the star, carving a narrow channel. The star's outer layers, meanwhile, are being disrupted. In many cases, a supernova explosion occurs simultaneously, driven by the energy deposited by the jets and the neutrinos from the initial collapse. The star is literally being torn apart from the inside, while the jets bore through it. The jets break through the surface of the star and erupt into space. Internal shocks within the jets produce intense gamma-ray emission. The burst begins. For anywhere from a few seconds to several minutes, gamma rays pour out of the jet in our direction, if we happen to be in the path of the beam. The light curve is complex and variable, reflecting the turbulent, chaotic nature of the jet. As the jet plows into the surrounding interstellar medium, it decelerates and produces a broadband afterglow that fades over days and weeks. Optical telescopes, X-ray telescopes, and radio telescopes detect this afterglow, allowing astronomers to pinpoint the location and distance of the burst. The entire active phase, from the moment the core collapses to the moment the jets shut off, typically lasts between 10 seconds and a few minutes. Everything that produces the gamma-ray burst, the formation of a black hole, the creation of an accretion disk, the launching and breakout of relativistic jets, happens in roughly the time it takes you to brush your teeth. In that brief window, those two narrow beams carry more energy than 1,000 ordinary supernovae release as visible light. The sheer concentration of energy into such a short time scale and such a narrow beam is what makes it the most violent phenomenon in the observable universe. The collapsar model has been confirmed by observations in multiple ways. Astronomers have detected supernovae associated with long-duration gamma-ray bursts, confirming that the bursts come from dying massive stars. They've observed the afterglows and host galaxies, confirming the distances and environments predicted by the model. They've measured the properties of the jets, the opening angles, velocities and energies, and found them consistent with the predictions. The model isn't speculation. It's supported by decades of observational evidence. But here's what's extraordinary. The collapsar mechanism isn't the only way to produce a gamma-ray burst. There's a second path, a completely different type of cosmic catastrophe that produces the same result. It doesn't involve a dying star at all. It involves something even more exotic. Two of the densest objects in the universe, objects left behind by previous stellar explosions, spiraling toward each other across millions of years, and finally colliding in an event so violent that it warps the very fabric of space-time itself. And when astronomers finally detected this second type of event, in both light and gravitational waves simultaneously, it didn't just confirm a theory. It opened an entirely new way of observing the universe. The collapsar model explains how the death of a massive star can produce a gamma-ray burst. A rapidly spinning core collapses into a black hole. An accretion disk forms. Magnetic fields wind up and launch relativistic jets. And those jets punch through the dying star and blast gamma rays across the cosmos. It's an elegant and well-supported explanation. But it has a problem. It doesn't explain all gamma ray bursts. Because when astronomers studied the full catalogue of gamma-ray bursts detected over the decades, they noticed something important. The bursts fall into two distinct categories, and the collapsar model only accounts for one of them. The division is based on duration. Some gamma-ray bursts last longer than about 2 seconds. These are the long-duration bursts, and they're the ones explained by the collapsar model, the ones produced by dying massive stars. But a significant fraction of gamma-ray bursts, roughly about 30%, last less than 2 seconds. Some last only a few milliseconds, a few hundredths of a second. A flash so brief that if you blinked, you'd miss it entirely. Except that this blink carries more energy than most stars produce in their entire lifetimes. These short-duration gamma-ray bursts are different from their longer cousins in several important ways beyond just their duration. Their gamma-ray spectra tend to be harder, meaning the gamma rays they produce are on average more energetic. They occur in different types of galaxies. Long-duration bursts, as we discussed, tend to occur in small, irregular galaxies with active star formation, the kinds of galaxies where massive young stars are being born and dying rapidly. Short-duration bursts, by contrast, occur in all types of galaxies, including large elliptical galaxies where star formation stopped billions of years ago. Some short-duration bursts occur far from the centers of their host galaxies, out in the suburbs where very few stars exist. This was a huge clue. If short-duration bursts came from dying massive stars, you'd expect to find them in regions of active star formation, near the young stellar populations where massive stars live and die. Instead, many of them were found in old stellar environments, in galaxies dominated by ancient stars. Whatever was producing these short bursts didn't require a young, massive star. It could happen in old stellar populations. It could happen far from where stars are being born. It could happen billions of years after the last burst of star formation in a galaxy. Astronomers realized there had to be a second mechanism, a completely different type of catastrophe that could produce relativistic jets and gamma rays without involving the death of a massive star. And the leading candidate was something extraordinary: the merger of two neutron stars. To understand why this idea made sense, you need to understand what neutron stars really are. Because neutron stars are among the most extreme objects in the entire universe, and everything about them pushes the boundaries of known physics. A neutron star is what's left behind when a star between about 8 and 25 solar masses explodes as a supernova. The outer layers of the star are blasted into space, but the core survives as an incredibly dense ball of neutrons. We talked about this earlier. But let me go deeper into what this object actually is, because the numbers are genuinely difficult to absorb. A typical neutron star has a mass of about 1.5 times the mass of the Sun. All of that mass, 1.5 suns worth, is compressed into a sphere roughly 20 kilometers across. That's about the size of a mid-sized city. Imagine taking a star, an object 864,000 miles wide, and crushing it down until it fits inside a space about 12 miles across. The density is beyond anything you encounter in normal experience. A single teaspoon of neutron star material would weigh roughly 4 billion tons. That's more than the combined weight of every vehicle on Earth, every car, every truck, every bus, every train, packed together and then multiplied several times over. If you could somehow bring a teaspoon of neutron star material to Earth's surface, it would fall through the ground like a bullet through tissue paper, boring straight through the planet. The gravity at the surface of a neutron star is about 2 billion times stronger than gravity at the surface of Earth. If you dropped an object from a height of 1 meter above a neutron star's surface, it would hit the surface traveling at roughly 700,000 kilometers per hour. The escape velocity, the speed you'd need to reach to leave the surface, is about 100,000 kilometers per second. That's roughly a third the speed of light. To escape a neutron star, you'd need to be traveling at a third the speed of light. For comparison, the escape velocity from Earth's surface is only about 11 kilometers per second. Neutron stars also spin incredibly fast. When the core of the star collapses from Earth-sized to city-sized, conservation of angular momentum causes it to spin up dramatically, the same way a spinning ball of pizza dough speeds up when the chef pulls it inward with their hands. A star that was rotating once every few weeks can become a neutron star spinning hundreds of times per second. The fastest known neutron star, a pulsar called PSRJ 1748-2446 AD, rotates 716 times per second. Think about that. An object with more mass than the Sun, compressed to the size of a city, spinning 716 times every single second. A point on its equator is moving at roughly a fifth the speed of light. The centrifugal forces at the surface are enormous, but the gravity is so strong that the star holds together. The magnetic fields of neutron stars are equally extreme. A typical neutron star has a magnetic field roughly 1 trillion times stronger than Earth's. Some neutron stars called magnetars have magnetic fields 1,000 times stronger still, reaching 1 quadrillion times Earth's field strength. These magnetic fields are so powerful that at close range they would distort the shapes of atoms, stretching them into thin cylinders aligned with the field lines. At even closer range, the magnetic field would be lethal, disrupting the chemistry of your body at a molecular level. These are the objects we're talking about when we discuss neutron star mergers. Two of these ultra-dense, rapidly spinning, intensely magnetic remnants of dead stars, each carrying more mass than the sun in a volume you could drive across in minutes, spiraling toward each other and colliding. But how do two neutron stars end up on a collision course? The answer involves billions of years of cosmic choreography. It starts with two massive stars orbiting each other. Binary star systems are actually quite common. About half of all stars in the Milky Way exist in binary or multiple star systems, gravitationally bound to one or more companion stars. When both stars in a binary system are massive enough to produce supernovae, interesting things happen. The more massive star evolves faster and explodes first, leaving behind a neutron star. The supernova explosion is asymmetric, meaning it gives the neutron star a kick, a velocity boost in a random direction. In many cases, this kick disrupts the binary. The neutron star goes flying off in one direction, and the surviving companion star goes another way. The system is destroyed, but sometimes, if the kick is small enough, or aimed in the right direction, the binary survives. The neutron star remains gravitationally bound to its companion, now orbiting a normal star. Eventually, the second star also evolves, swells, and explodes as its own supernova. Again, there's a kick. Again, the system might be disrupted. But if it survives this second explosion, you're left with two neutron stars orbiting each other. A binary neutron star system. These systems are rare. Both stars had to be massive enough to produce neutron stars, both supernovae had to leave the binary intact, and the resulting orbits had to be close enough for what comes next to matter. What comes next is a slow, patient, inevitable process. The two neutron stars orbit each other, and as they do, they emit gravitational waves. Gravitational waves are ripples in the fabric of space-time itself. Predicted by Einstein's general theory of relativity in 1915, and first directly detected by the LIGO experiment in 2015, exactly 100 years later. Any two objects orbiting each other emit gravitational waves, but for most systems the effect is negligibly small. For two neutron stars in a close orbit, however, the gravitational wave emission is significant. Here's the crucial point. Gravitational waves carry energy away from the system. As the binary emits gravitational waves, it loses orbital energy. And when a binary system loses orbital energy, the orbit shrinks. The two objects spiral closer together. As they get closer, they orbit faster. As they orbit faster, they emit gravitational waves more intensely, which causes them to lose energy faster, which causes them to spiral inward faster. It's a runaway process. An accelerating death spiral that can only end one way. But the timescale is long. Incredibly long. A typical binary neutron star system might take hundreds of millions or even billions of years to spiral together. The orbital decay is slow at first, imperceptible over human timescales. The Hulse-Taylor binary pulsar, discovered in 1974, consists of two neutron stars orbiting each other with a period of about 7.75 hours. Precise measurements over decades have shown that the orbital period is decreasing by about 76 microseconds per year, exactly as predicted by general relativity for gravitational wave emission. At this rate, the two neutron stars will merge in about 300 million years. They've been spiraling toward each other for far longer than that, and they still have hundreds of millions of years to go. But eventually, inevitably, the two neutron stars get close enough that the final act begins. And the final act is fast. Astonishingly fast. In the last few minutes of the inspiral, the two neutron stars are separated by only a few hundred kilometers, orbiting each other hundreds of times per second. Each neutron star is about 20 kilometers across, and they're only a few body lengths apart, whipping around each other at a significant fraction of the speed of light. The gravitational wave emission at this point is enormous. More energy is being radiated as gravitational waves in these final minutes than the sun will emit in its entire lifetime. The frequency and amplitude of the gravitational waves are increasing rapidly, producing what physicists call a chirp, a rising tone that sweeps upward in both pitch and volume as the neutron stars spiral closer and closer. In the final milliseconds, the neutron stars are essentially touching. Their surfaces are being distorted by tidal forces, stretched and deformed by each other's immense gravity. Material is being ripped from their surfaces. The tidal forces are so extreme that the neutron stars are no longer spherical. They're being pulled into elongated shapes, like cosmic water droplets stretching toward each other. And then they collide. Two objects, each containing more mass than the sun, each compressed to the density of an atomic nucleus, slam into each other at roughly a third the speed of light. The collision is almost instantaneous. In less than a millisecond, the two neutron stars merge into a single, violently oscillating, impossibly hot object. What happens next depends on the total mass of the merged object. If the combined mass is below a certain threshold, roughly 2.8 solar masses, though the exact number depends on the equation of state of ultra-dense matter, which we don't know precisely, the merged object might briefly survive as what's called a hypermassive neutron star. This is a neutron star that's more massive than any neutron star could normally support. It's held up temporarily by its rapid rotation and by thermal pressure from the enormous heat generated by the collision, but it's unstable. It can't last. Within milliseconds to perhaps a few hundred milliseconds, the hypermassive neutron star collapses into a black hole. If the combined mass is above this threshold, the collapse to a black hole happens almost immediately. There's no intermediate phase. The merged object goes straight from two neutron stars to a black hole in a fraction of a millisecond. Either way, the end result is the same. A rapidly spinning black hole surrounded by a disk of extremely hot, extremely dense material. The debris from the collision, the material that was flung outward by the violence of the merger but didn't escape, settles into an accretion disk around the newborn black hole. And now we're back to familiar territory. A spinning black hole with an accretion disk. The same setup as the collapsar model. Magnetic fields threading through the disk get wound up by the black hole's rotation. The Blandford-Znajek mechanism extracts rotational energy from the black hole. Twin relativistic jets are launched along the spin axis, moving at more than 99% the speed of light. But there are important differences from the collapsar case. In a collapsar, the jets have to drill through the massive outer layers of a dying star. That takes 10 to 20 seconds, and the central engine has to remain active the entire time. In a neutron star merger, there's no star to punch through. The merger happens in open space, far from any stellar envelope. The jets can emerge freely almost immediately. There's also much less material available to feed the accretion disk. In a collapsar, an entire massive star is collapsing and feeding the black hole. In a neutron star merger, the only available material is the debris from the collision itself, and much of that gets swallowed quickly. This is why short-duration gamma-ray bursts are short. The central engine runs out of fuel fast. The accretion disk is smaller and drains more quickly. The jets fire for a brief time, typically less than 2 seconds, often only a fraction of a second, and then shut off. The burst is over almost before it begins, but in that fraction of a second, the energy output is still enormous. A short gamma-ray burst might release 10 to the 42 to 10 to the 43 joules in gamma rays, comparable to or only slightly less than a long-duration burst in terms of power output per second. The violence per unit time is actually similar. It's just that the event is shorter because there's less fuel. But the merger produces something else as well. Something that long-duration bursts from dying stars do not. When two neutron stars collide, not all of the material falls into the black hole. A significant fraction, perhaps 1 to 10% of a solar mass, is flung outward in all directions by the violence of the collision. This material is incredibly neutron-rich, meaning it contains a huge excess of neutrons compared to protons. And as this neutron-rich material expands outward and cools, something remarkable happens. The neutrons rapidly capture onto atomic nuclei in a process called the R process, where the R stands for rapid. This rapid neutron capture builds up heavier and heavier elements, forging atoms that cannot be created in any other known environment. This is where the heaviest elements in the universe are made: gold, platinum, uranium, thorium, all the elements at the bottom of the periodic table, the ones too heavy to be produced by fusion in stellar cores, or even by ordinary supernovae, are forged here, in the expanding debris cloud of a neutron star merger. The amount of heavy elements produced is staggering. A single neutron star merger can produce several Earth masses worth of gold, roughly 10 Earth masses of platinum, enough precious metals to put a price beyond any human concept of wealth. The gold atom in your wedding ring, the platinum in a catalytic converter, the uranium in a nuclear reactor. Almost certainly, most of it was forged in collisions like these, billions of years ago, long before our solar system formed. The expanding debris cloud glows. The radioactive decay of the freshly forged heavy elements heats the material, causing it to emit light. This glow is called a kilonova. The name is a reference to the fact that it's roughly 1,000 times brighter than an ordinary nova, but much fainter than a supernova. A kilonova is not as bright as a supernova, but it's still visible across enormous distances. It typically peaks in brightness a few days after the merger and fades over the following weeks. The color of the kilonova evolves as it expands and cools, starting relatively blue and shifting toward red and infrared as the heavier elements in the debris become more dominant in determining the opacity of the expanding cloud. The kilonova is important because it's visible from all directions, not just along the jet axis. A gamma-ray burst can only be seen if you happen to be directly in the path of the beam, but a kilonova radiates in all directions, making it detectable regardless of the jet's orientation. This means that for every short gamma-ray burst we detect, there are many more neutron star mergers happening where the jet isn't aimed at us. We miss the gamma-ray burst, but we might still see the kilonova. All of this The two-channel model with collapsars producing long bursts and neutron star mergers producing short bursts was a well-developed theoretical framework by the early 2000s. But it was still largely theoretical. The evidence was circumstantial. Astronomers had good reasons to believe the models were correct, but they hadn't directly observed a neutron star merger in enough detail to confirm it beyond doubt. That changed on August 17th, 2017, in what became one of the most important astronomical observations in history. On that day, two detectors in the LIGO experiment, one in Hanford, Washington, and one in Livingston, Louisiana, along with the Virgo detector in Italy, picked up a gravitational wave signal. This wasn't the first gravitational wave detection. LIGO had detected gravitational waves from merging black holes starting in 2015, but this signal was different. It lasted much longer than the black hole merger signals. Instead of a brief chirp lasting a fraction of a second, this signal lasted about 100 seconds, sweeping upward in frequency as two objects spiraled together. The longer duration indicated that the merging objects were less massive than black holes. The signal was consistent with two neutron stars, each with a mass of roughly 1.2 to 1.6 solar masses, spiraling together and colliding. The event was designated GW170817. The gravitational wave signal told astronomers several things immediately. The masses of the two objects, which were consistent with neutron stars, the distance, about 130 million light-years, in a relatively nearby galaxy, and the approximate location on the sky narrowed down to a region of about 28 square degrees. But then, 1.7 seconds after the gravitational wave signal peaked, the Fermi Gamma Ray Space Telescope detected a short gamma ray burst from the same region of sky, 1.7 seconds. The gravitational waves arrived, signaling the merger of two neutron stars, and less than 2 seconds later, gamma rays arrived, signaling a gamma ray burst. This was the confirmation astronomers had been waiting for. Neutron star mergers produce short gamma ray bursts. The theoretical prediction, developed over decades, was correct. What followed was the most intensive observational campaign in the history of astronomy. Within hours, dozens of telescopes around the world and in space swung to the source location. The host galaxy was identified as NG C4993, a lenticular galaxy about 130 million light-years away, in the constellation Hydra. A quiet, early-type galaxy with little ongoing star formation, exactly the kind of old stellar environment where neutron star mergers were predicted to occur. Optical telescopes detected the kilonova. It appeared as a new point of light near the galaxy, visible in the hours and days following the merger. The kilonova started out blue and bright, then reddened and faded over the following days and weeks, exactly as theoretical models had predicted. Spectroscopic observations of the kilonova revealed the signatures of heavy elements, including the fingerprints of newly forged strontium, confirming that R-processed nucleosynthesis was occurring in the expanding debris. The kilonova observations confirmed that neutron star mergers are indeed the cosmic forges where the heaviest elements are created. X-ray and radio observations detected the afterglow of the gamma ray burst, confirming the presence of a relativistic jet. But the afterglow was unusual. It was much fainter than expected, and it brightened over the weeks following the merger rather than fading immediately. This suggested that the jet wasn't aimed directly at Earth. Instead, Earth was slightly off-axis, viewing the jet from the side. As the jet decelerated and spread out, more of its radiation became visible from off-axis angles, causing the apparent brightening. This was the first time astronomers had observed an off-axis gamma-ray burst, and it confirmed another theoretical prediction. We only see the full fury of a gamma-ray burst when we're looking straight down the jet. From the side, the burst appears much weaker. The total number of observatories that participated in the follow-up campaign exceeded 70. Telescopes spanning every wavelength of light, from gamma rays to radio waves, observed the event. Papers were published by thousands of scientists across dozens of countries. It was, without exaggeration, the most comprehensively observed single astrophysical event in the history of science. GW170817 confirmed multiple theoretical predictions simultaneously. It confirmed that binary neutron star mergers produce short gamma-ray bursts. It confirmed that these mergers produce kilonovae. It confirmed that R-process nucleosynthesis occurs in the merger debris, creating heavy elements like gold and platinum. It confirmed that gravitational waves travel at the speed of light to extraordinary precision by showing that the gravitational waves and the gamma rays arrived within 1.7 seconds of each other after traveling 130 million light years. And it confirmed that gravitational wave astronomy could work in tandem with traditional electromagnetic astronomy, opening an entirely new era of what scientists call multi-messenger astrophysics. This last point deserves emphasis. Before GW170817, astronomers observed the universe almost entirely through light, electromagnetic radiation in its various forms. Gravitational waves offered a completely new way to observe the cosmos, a way to detect events that might produce little or no light, like black hole mergers. But the real power comes from combining both. When you observe an event in both gravitational waves and light, you get information that neither one alone could provide. The gravitational waves tell you about the masses and dynamics of the merging objects. The light tells you about the environment, the elements being produced, the jet structure, and the host galaxy. Together they give you a complete picture that's far richer than either view alone. GW170817 was also used to make an independent measurement of the expansion rate of the universe. By combining the gravitational wave signal, which gives you the absolute distance to the source, with the redshift of the host galaxy, which tells you how fast the galaxy is receding, astronomers calculated the Hubble constant, the rate at which the universe is expanding. This measurement was independent of all previous methods and provided a valuable new data point in the ongoing debate about the exact value of the Hubble constant. The detection of GW170817 was a watershed moment. It tied together gravitational wave physics, nuclear physics, astrophysics, and cosmology into a single observation. It confirmed decades of theoretical work, and it showed that the universe's most violent short-duration explosions come from the collisions of the most extreme objects in existence, objects so dense that their gravity warps the light passing near them, objects where time itself runs measurably slower at their surfaces, objects that spin hundreds of times per second while generating magnetic fields trillions of times stronger than anything on Earth. When two of these objects collide, the result is a catastrophe so extreme that it shakes the fabric of space-time itself while simultaneously forging the heaviest atoms in the universe and launching jets of plasma at nearly the speed of light. two completely different cosmic catastrophes, two completely different paths, a massive star collapsing and a pair of neutron stars merging, both producing the same terrifying outcome: a newborn black hole, an accretion disk, relativistic jets, and a blinding flash of gamma rays detectable across billions of light years. But the question remains: why are these the most violent explosions in the universe? What is it specifically about the concentration of energy, about the physics of relativistic beaming, about the time scale and intensity of these events that puts them beyond anything else the cosmos has to offer? The answer lies in understanding exactly what happens when you compress unimaginable energy into a beam only a few degrees wide, moving at 99.9% the speed of light, and release it all in a matter of seconds. We've now seen both paths that lead to a gamma ray burst, and at first glance they couldn't be more different. One takes millions of years of stellar evolution and ends in a core collapse lasting less than a second. The other takes billions of years of orbital decay and ends in a collision lasting less than a millisecond. Yet both funnel their catastrophic energy through the same physical engine, a spinning black hole and accretion disk, into the same terrifying output: relativistic jets. But we still haven't fully answered the central question: why are gamma ray bursts the most violent explosions in the universe? What specifically makes them worse than a supernova, more extreme than a quasar, more concentrated than anything else the cosmos can produce? The answer comes down to three things working together: the total energy involved, the concentration of that energy into a narrow beam, and the absurdly short timescale over which it's all released. Each of these factors alone would make gamma ray bursts remarkable. Together, they make gamma ray bursts unmatched. Let's start with the beaming, because this is the factor that most people misunderstand, and it's the one that truly sets gamma ray bursts apart from every other violent event in the universe. We talked earlier about how a gamma ray burst concentrates its energy into a narrow jet rather than radiating in all directions. We use the analogy of a laser versus a light bulb. But now let's go deeper into the physics of why this matters, because the effect is far more dramatic than a simple flashlight analogy can convey. The jets in a gamma ray burst are moving at what physicists call ultra-relativistic speeds. The material in the jet isn't just moving fast, it's moving at 99.9% the speed of light, or faster. At these speeds, the physics of special relativity produces effects that are profoundly counterintuitive. One of the most important is called relativistic beaming, and it fundamentally changes how the radiation from the jet appears to an observer. To understand relativistic beaming, you need to understand something called the Lorentz factor. The Lorentz factor is a number that describes how extreme the relativistic effects are for an object moving at a given speed. It's calculated from the velocity, and it tells you how much time dilation, length contraction, and radiation beaming the object experiences. At everyday speeds, the speeds of cars and planes, and even rockets, the Lorentz factor is essentially 1. And relativistic effects are negligible. You'd never notice them. At 90% the speed of light, the Lorentz factor is about 2.3. At 99%, it's about 7. At 99.9%, it's about 22. And at 99.99%, it's about 71. The Lorentz factors in gamma ray burst jets are typically between 100 and 1000. That means the jet material is moving so unfathomably close to the speed of light that relativistic Effects are amplified by factors of hundreds or more. At a Lorentz factor of 300, which is typical for many observed bursts, the jet material is moving at 99.9994% the speed of light. The difference between the jet's velocity and the speed of light itself is vanishingly small, and this tiny remaining gap is what produces the extreme beaming effects. Here's what a Lorentz factor of several hundred does to the radiation emitted by the jet. Imagine the jet is emitting radiation in all directions from its own perspective. In the jet's own frame of reference, the radiation goes out uniformly. But from our perspective, watching the jet approach at nearly the speed of light, all of that radiation gets compressed into a narrow cone aimed in the direction the jet is moving. The opening angle of this cone is roughly 1 divided by the Lorentz factor, measured in radians. For a Lorentz factor of 100, the radiation is compressed into a cone only about 0.6 degrees wide. All the energy that was spread across the full sphere in the jet's frame gets squeezed into a tiny cone in our frame. This has 2 dramatic consequences. First, the radiation is concentrate. Energy that would have been spread over the entire sky is instead aimed directly at you. The intensity, as the energy per unit area hitting your detector, is amplified enormously. Second, the photons themselves are blue shifted. Their frequencies increase and their energies go up. Radiation that might have been emitted as X-rays in the jet's frame arrives as gamma rays in our frame because the relativistic motion has boosted the energy of each individual photon. The net effect is that the apparent luminosity of the jet, when viewed head-on, is amplified by a factor proportional to the Lorentz factor raised to a high power. For typical gamma-ray burst parameters, the apparent brightness can be thousands or even tens of thousands of times greater than the actual total luminosity of the source. This is why early calculations suggested gamma-ray bursts were releasing the energy equivalent of converting an entire sun into pure energy. They weren't. They were releasing far less total energy than that, but the beaming compressed all that energy into such a narrow cone that looking down the barrel of the jet, the apparent brightness was extraordinary. Think of it this way. Imagine you have a garden hose connected to a normal water supply. The total amount of water flowing through the hose is modest. But if you put your thumb over the end and squeeze the water into a narrow stream, the force of that stream at the point of impact is enormous. Enough to sting your skin, enough to blast dirt off a driveway, enough to push objects around. The total water hasn't changed, but the concentration has. Now imagine doing the same thing, but instead of water, you're concentrating the energy output of a stellar catastrophe. Instead of a garden hose, you have a jet carrying energy comparable to a supernova. And instead of squeezing it with your thumb, you're compressing it with the physics of special relativity into a beam less than a degree wide. The energy density at the point of impact is beyond anything else in the universe. Let me put some concrete numbers on this. A typical supernova releases about 10 to the 44 joules of kinetic energy in its expanding debris, and about 10 to the 42 joules as visible light. This energy is radiated roughly equally in all directions. So the energy per unit solid angle, the amount of energy aimed at any particular patch of sky, is relatively modest. A gamma ray burst, by contrast, might release a similar total amount of energy, perhaps 10 to the 44 joules, but that energy is concentrated into a jet that covers only about 1,000th of the full sky. This means the energy per unit solid angle is roughly 1,000 times higher than a supernova's. And the Lorentz factor, amplification, pushes the apparent brightness even higher for observers in the beam. But total energy and beaming are only part of the story. The third factor is time. Because a gamma ray burst doesn't just release enormous concentrated energy, it does so in an absurdly short period. A supernova unfolds over weeks, the star explodes, and the expanding debris shines for days and weeks as it cools. The peak brightness lasts for roughly 2 to 3 weeks. The total energy is released gradually, spread out over a long time scale. A gamma ray burst, by contrast, releases most of its gamma ray energy in seconds. Some long duration bursts last a few minutes. Some short duration bursts last less than a second. The energy per unit time, the power, is therefore vastly greater than a supernova's. Even if a gamma ray burst and a supernova release the same total energy, the fact that the burst does it in seconds rather than weeks means the instantaneous power is millions of times higher. Let me combine all three factors. Consider a long duration gamma ray burst lasting about 20 seconds, releasing about 10 to the 44 joules of energy concentrated in a jet, covering 1,000th of the sky. The isotropic equivalent luminosity, what the burst would appear to release if it were radiating equally in all directions, can reach 10 to the 47 joules per second. That's about 100 billion times the luminosity of the sun. For those 20 seconds, the gamma ray burst outshines the entire observable universe in gamma rays. Not a galaxy, not a supercluster, the entire observable universe. 2 trillion galaxies, each containing hundreds of billions of stars, and a single event on one dying star briefly outshines them all. Nothing else in the cosmos comes close to this combination of factors. Supernovae release comparable total energy, but spread it over weeks and in all directions. Active galactic nuclei and quasars, powered by supermassive black holes, consuming matter at the centers of galaxies, can be extraordinarily luminous, outshining entire galaxies for millions of years. But their energy is spread over long timescales and broader emission patterns. They're marathon runners. Gamma ray bursts are sprinters. The total energy of a quasar emitted over millions of years dwarfs a gamma ray burst. But the instantaneous concentrated power of a gamma ray burst exceeds everything. Magnetar flares come closest. Magnetars are neutron stars with extraordinarily powerful magnetic fields. Occasionally, the magnetic field undergoes a catastrophic rearrangement, releasing a burst of energy in a fraction of a second. The most powerful magnetar flare ever detected came from SGR 1806-20 on December 27th, 2004. In about 0.2 of a second, this magnetar released as much energy as the sun produces in about 250,000 years. It was so bright that it measurably affected Earth's upper atmosphere from 50,000 light years away, halfway across the galaxy. That's impressive. But even this extreme event was roughly tens of thousands of times less luminous than a typical gamma ray burst. Magnetar flares are terrifying, but gamma ray bursts are on an entirely different level. So what would happen if a gamma ray burst occurred nearby? Not billions of light years away, but close, within our own galaxy, pointed at Earth. This question isn't purely hypothetical. Astronomers have seriously studied this scenario, and the results are sobering. If a gamma ray burst occurred within about 6,500 light years of Earth, roughly the distance to some well-known stars and nebulae in our region of the galaxy, and if one of its jets happened to be aimed directly at us, the consequences would be catastrophic. The initial flash of gamma rays would last only seconds or minutes, but in those seconds, the burst would deliver an enormous dose of high-energy radiation to the side of Earth facing the event. The gamma rays themselves wouldn't reach the ground. Earth's atmosphere is thick enough to absorb gamma rays, which is why we need space-based telescopes to study them. But the gamma rays wouldn't harmlessly vanish upon hitting the atmosphere. Instead, they would trigger a cascade of chemical reactions in the upper atmosphere. The gamma ray photons would break apart molecular nitrogen and oxygen, the two gases that make up most of our atmosphere. The fragments would recombine into nitrogen oxides, particularly nitric oxide and nitrogen dioxide. These nitrogen oxide compounds would then attack the ozone layer. The ozone layer sits in the stratosphere, about 15 to 35 kilometers above the surface. It absorbs most of the sun's ultraviolet radiation, particularly the most dangerous ultraviolet C and ultraviolet B wavelengths. Without the ozone layer, this radiation would reach the surface at full intensity. Ultraviolet C radiation is lethal to most surface life. It damages DNA directly, causing mutations and cell death. Ultraviolet B radiation causes sunburn, skin cancer, cataracts, and suppresses immune systems. A nearby gamma ray burst could destroy up to 75% of the ozone layer in the hemisphere facing the burst. The nitrogen oxides produced by the gamma rays would persist in the stratosphere for years, continuing to destroy ozone long after the initial flash. Recovery of the ozone layer would take a decade or more. During that decade, surface life would be exposed to dramatically increased ultraviolet radiation. The increase would not be subtle. Models suggest that ultraviolet B radiation at the surface could increase by a factor of 3 or more across the affected hemisphere. Phytoplankton in the oceans, the microscopic organisms that form the base of the marine food chain and produce roughly half of Earth's oxygen through photosynthesis, would be severely impacted. Phytoplankton are particularly sensitive to ultraviolet radiation because they live at or near the ocean surface, where they're directly exposed. They have no way to hide, no way to burrow underground or seek shade. A collapse of phytoplankton populations would ripple through the entire marine food chain. Zooplankton that feed on phytoplankton would starve. Fish that feed on zooplankton would decline. Marine mammals and seabirds that depend on fish would follow. The entire oceanic ecosystem could unravel from the bottom up. On land, increased ultraviolet radiation would stress plants and animals. Many species would suffer increased DNA damage, reduced reproductive success, and weakened immune responses. The combined effect, a decimated ozone layer, increased ultraviolet radiation, collapsing marine food chains, and stressed terrestrial ecosystems, could trigger a mass extinction event. And this isn't just speculation. Some scientists have proposed that exactly this kind of event may have already happened in Earth's history. About 445 million years ago, at the end of the Ordovician period, Earth experienced one of the 5 major mass extinctions in its history. The late Ordovician extinction wiped out roughly 85% of all marine species. At the time, most complex life on Earth lived in the oceans. So a marine extinction was effectively a global catastrophe. The cause of the Ordovician extinction has been debated for decades. The leading traditional explanation involves glaciation. There's evidence that a major ice age occurred at the end of the Ordovician, driven by a drop in carbon dioxide levels, or changes in ocean circulation. But the glaciation hypothesis has some difficulties. The extinction happened in two distinct pulses separated by roughly 1 million years, which is hard to explain with a single glaciation event. In 2004, astrophysicists Adrian Malott and Brian Thomas published a paper proposing that a nearby gamma-ray burst could explain many features of the Ordovician extinction. They argued that a burst within about 6,000 light-years could have destroyed enough ozone to cause the kind of a marine extinction observed. The initial gamma-ray pulse would have depleted the ozone layer rapidly, exposing surface organisms to lethal ultraviolet radiation. Phytoplankton die-offs would have collapsed food chains. The nitrogen dioxide produced in the upper atmosphere would have also caused a brief period of global cooling by blocking sunlight, potentially triggering the glaciation that's been observed in the geological record. This hypothesis is not proven. It remains one of several competing explanations for the Ordovician extinction. There's no direct evidence that a gamma-ray burst occurred at that time, no telltale chemical signature preserved in the rocks that would definitively identify a burst. But the hypothesis is physically plausible. Gamma-ray bursts do occur. They are powerful enough to cause the kind of damage described, and statistically, it's likely that Earth has been hit by the jet of a nearby burst at some point in its 4.5 billion year history. The question isn't whether it could happen. It's whether it has happened and whether we would recognize the evidence if it had. Should we be worried about a gamma-ray burst hitting Earth? The honest answer is not particularly. The odds are extremely low. Most gamma-ray bursts we observe occur in distant galaxies billions of light years away. They're cosmological events happening across enormous distances. Within the Milky Way, the conditions for producing a gamma-ray burst, a rapidly rotating massive star with low metallicity in the case of long-duration bursts, are relatively rare. Most massive stars in our galaxy have too much metallicity and too little rotation to produce the collapsar jets. Short-duration bursts from neutron star mergers could theoretically occur anywhere, but the jet would need to be aimed directly at Earth, and the odds of that alignment are small. Even if a gamma-ray burst occurred somewhere in the Milky Way, the jet covers only a tiny fraction of the sky. A jet with a half-opening angle of a few degrees covers only about 1/500th of the total sky. So even if a burst went off in our galaxy, the chances that one of its two jets would be aimed at Earth are roughly 1 in a few hundred, and the burst would also need to be close enough to cause damage within a few thousand light years. Combining all these factors, the probability of a damaging gamma-ray burst hitting Earth in any given century is estimated at roughly 1 in a few 100 million. It's not zero. Over billions of years it might happen once or twice, but it's not something to lose sleep over tonight. Statistically, you're far more likely to be struck by lightning than to be affected by a gamma-ray burst. The universe contains many dangers, but this particular one is extremely unlikely to affect us in any human-relevant timescale. But the fact that it could happen at all tells us something profound about the universe we live in. The cosmos is not a gentle place. It operates on scales of violence that dwarf human comprehension. Somewhere in the observable universe, roughly once per day, a gamma-ray burst goes off. Every single day, somewhere out there, a massive star collapses or two neutron stars collide. And for a brief instant, a beam of destruction carries more concentrated power than anything else in the cosmos. These events happen in galaxies billions of light years away, too far to affect us, but they happen constantly. The universe is perpetually producing explosions of this magnitude, has been producing them for billions of years, and will continue producing them for billions of years to come. And yet, the mechanisms behind these events are governed by the same physics we study in laboratories on Earth. The same electromagnetic theory that explains how a battery powers a flashlight explains how magnetic fields launch relativistic jets. The same general relativity that predicts how GPS satellites need to correct for time dilation explains how spinning black holes drag space-time and extract rotational energy. The same nuclear physics that explains radioactive decay explains the R-process nucleosynthesis in kilonova debris. The same special relativity that predicts time dilation in particle accelerators explains why gamma-ray burst jets appear so extraordinarily bright through relativistic beaming. There's something beautiful about this. The most extreme events in the universe, events that release more concentrated energy than anything else nature can produce, are governed by the same laws of physics that operate here on Earth. There's no special physics for extreme events. There's no separate set of rules for the most violent phenomena. The equations we've written down in our textbooks, the formulas derived by Einstein and Maxwell and Dirac and all the others, those same equations describe both the gentle fall of an apple from a tree and the catastrophic collapse of a star into a black hole, launching jets at 99.9% the speed of light. The universe has one set of rules, and those rules operate across a range of conditions so vast that the human mind struggles to hold both ends of the spectrum simultaneously. Gamma-ray bursts also remind us how much we've learned in a remarkably short time. In 1967, the first gamma-ray burst was detected by accident by satellites designed to watch for nuclear weapons tests. Nobody knew what it was. Nobody even knew such events existed. In the decades that followed, astronomers gradually pieced together the puzzle. They determined the distances. They developed the collapsar and merger models. They observed afterglows and host galaxies. They detected gravitational waves from a neutron star merger, and saw the corresponding gamma-ray burst and kilonova. In barely 50 years, we went from complete ignorance to a detailed physical understanding of the most violent explosions in the universe. This progress was achieved by humans, small beings on a small planet orbiting an ordinary star in the suburbs of an ordinary galaxy. We built satellites and telescopes and gravitational wave detectors. We developed mathematical frameworks capable of describing the physics of relativistic jets and neutron star interiors and black hole accretion disks. We organized international collaboration spanning dozens of countries and hundreds of institutions. And we figured it out. We understood the most extreme events the universe can produce, not by going there, but by watching from our tiny vantage point billions of light years away and working out the physics. Every gamma-ray burst we detect is a message from the distant universe. A brief flash of light that has been traveling for billions of years, carrying information about a catastrophic event that happened long before our solar system existed. When we detect that flash, we're witnessing the death of a star or the collision of two neutron stars that occurred when the universe was younger, when Earth hadn't yet formed, when the atoms that would eventually become our planet and our bodies were still scattered across interstellar space. And yet, we can detect that flash, measure it, analyze it, and understand the physics that produced it. That's extraordinary. The most violent explosion in the universe isn't just a spectacle of destruction, It's a demonstration that the cosmos is knowable. The equations that describe a gamma ray burst fit on a single page. The physical principles behind the most violent event in the universe can be taught in a university classroom, and yet those same principles generate an explosion that can be detected from the edge of the observable universe. There's a profound tension in that, something almost paradoxical. The simplicity of the laws and the extremity of what they produce. A few elegant equations, and from them emerges the most concentrated violence nature is capable of. So, the next time you look up at the night sky and see the stars scattered across the darkness, remember what you've learned tonight. Some of those stars are massive enough that when they die, they won't simply fade away. They'll collapse, form black holes, and launch jets of destruction moving at nearly the speed of light. Somewhere out there, beyond the stars you can see, in galaxies so distant that their light has been traveling for billions of years, these events are happening right now. One every day on average. Each one producing more concentrated power per second than any other phenomenon in nature. Each one forging heavy elements, warping space-time, and launching beams of energy across billions of light years of space. The most violent explosion in the universe happens when nature takes the death of a star or the collision of two impossibly dense objects and concentrates the resulting energy into a beam so narrow, so fast and so intense that nothing else in the cosmos can match it. Not a supernova, not a quasar, not a magnetar flare, nothing. Gamma ray bursts sit alone at the very top of the scale of cosmic violence. They are the most extreme events we have ever detected. The most concentrated releases of energy the universe is capable of producing. And they operate through mechanisms so elegant that the same equations written on a chalkboard in a university lecture hall can describe them perfectly. The universe is vast. It is violent, it is beautiful, and it is comprehensible. That last fact might be the most extraordinary thing of all. We live in a universe that produces explosions powerful enough to sterilize solar systems from across the galaxy, and we can understand exactly how and why they happen. That understanding doesn't make the explosions less terrifying, but it does make them less mysterious. And in replacing mystery with understanding, we've done something remarkable. We've taken the most violent event in the cosmos and turned it into knowledge, into equations and observations and confirmed predictions, into a story we can tell. That's what science does. It takes the universe's most extreme phenomena, its most distant events, its most violent outbursts, and makes them knowable. Tonight, you've learned how a star's death or a neutron star collision can produce the most concentrated explosion in existence. You've learned why beaming and relativity amplify that explosion to apparently impossible brightness. You've learned that the gold in your jewelry was forged in one of these cataclysms. And you've learned that despite the terrifying scale of these events, the physics that governs them is the same physics that governs the world around you every day. The universe is not gentle, but it is understandable, and understanding it, even the most violent parts of it, is one of the most remarkable things our species has ever accomplished. Sleep well tonight, knowing that somewhere out there, a gamma ray burst is going off right now, and knowing that because of the work of thousands of scientists across decades of careful observation, you understand exactly what that means. Good night.